Most welcome. This video is a follow-up of my previous video on gamma function and beta function. I hope you have already watched that video. If not, the link is in the description below and you can see above as well. Now in this video, I shall solve 5 different types of problems, as you can see, which are appearing on your screen. And I will show you how you can solve problems or how you can evaluate integrals using gamma and beta functions. So I will solve basically this 5 problems. So now before I start solving the problems, let us quickly recollect the key points in gamma function and beta function that we discussed in our previous lecture. These 8 points, as I discussed in my previous video, that you cannot afford to forget if you wish to solve problems using gamma function and beta function. The first point is the definition of gamma function, that gamma x is equal to integral 0 to infinity e to the power minus t into t to the power x minus 1 dt when x is greater than 0. And you can see that the fourth point is the definition of beta function, that beta xy is equal to integral 0 to 1 t to the power x minus 1 into 1 minus t whole to the power y minus 1 dt when xy greater than 0. And all other properties can be proved from these definitions, as I had already discussed in my previous video. Now at this point you can pause the video and note down these 8 points in your copy if required. I hope you have noted down these 8 points. Now let us start solving our problems. The first one is evaluate integral 0 to infinity e to the power minus x square by 2 dx. You can understand this is an improper integral. So if you wish to make any substitution, you have to make it properly. That means, as I discussed in my lecture on improper integrals, if you have not watched that, the link is in the description below and you can see above as well. So let us try to do some substitution to get it in the form of gamma function. So let us substitute x square by 2 is equal to t in integral 0 to m e to the power minus x square by 2 dx, where this m is a positive real number. Then I can write that integral 0 to m e to the power minus x square divided by 2 dx will be equal to integral, we can understand when x is 0, t is 0, and when x is m, t will be m square by 2 e to the power minus t dx. Now if you consider our substitution, x square by 2 equal to t implies 2x divided by 2 dx equal to dt, which implies dx is equal to 1 upon x dt. Now 1 upon x will be under the root 2t, because x square by 2 is equal to t, so 1 upon root 2 t dt. So if I plug in everything here, what I'll be getting? I'll be getting 1 upon root 2t dt. So that means this is equal to, if I take this 1 upon root 2 common, then it will be integral 0 to m square divided by 2 e to the power minus t into t to the power minus half dt. Okay, now let me have some space here. So this will be equal to 1 upon root 2 integral 0 to m square divided by 2 e to the power minus t. Now t to the power minus half, I can write this as t to the power half minus 1 dt. Okay, interesting. Now if we let this m to approach to infinity, that means I am saying that letting this m approach to infinity, we get, so if we apply this on both the sides, we will get this side as integral 0 to infinity, let me have some space, integral 0 to infinity e to the power minus x square divided by 2 dx is equal to 1 upon root 2 integral 0 to infinity e to the power minus t to t to the power half minus 1 dt. Now remember that our definition for gamma function is gamma x is equal to integral 0 to infinity e to the power minus t into t to the power x minus 1 dt. So if we match this with this form, then can you tell me what we get? We get here our x as half. So this is nothing but 1 upon root 2 into gamma half. Now gamma half means root pi, as we have learned in our previous lecture. So this will be equal to under the root pi by 2. Can I write in this way? Root pi by root 2. So under the root pi by 2. So yes, this is our answer. Now let us solve the second problem. Evaluate integral 0 to pi by 2 1 up on square root of sin x dx into integral 0 to pi by 2 square root of sin x dx. Okay, so if we write it in a bit different way, then we can write the same integral as 0 to pi by 2 1 upon square root of sin x. That means I can consider this as sin to the power minus half x into 1. 1 means I can write this as cos to the power 0x dx into, in a similar way, this integral will become 0 to pi by 2. This is sin to the power half x. Again into 1 dx, I am writing 1 as cos to the power 0x dx. So yeah, you can understand, because I am writing in the integrand where both sine and cosine are present, so that I can compare with the form of beta function involving sine and cosine in the integral. That is, I am talking about the form beta xy equal to 2 into integral 0 to pi by 2 sine to the power 2x minus 1 theta cos to the power 2y minus 1 theta d theta, where x and y both are greater than 0. I am talking about this form. I am bringing in cosine also in the integrand because so that I can compare with this form. So if we compare with this form, so you can well understand that actually in this representation, this is my 2x minus 1 and this 0 is my 2y minus 1. So if 2x minus 1 is equal to minus half, then what I can write for x? So certainly x will be equal to 1 by 4, and if 2y minus 1 equal to 0, so y will be equal to half. So this integral in the first integral can be written as half into beta 1 by 4 comma 1 by 2 according to this particular formula. And similarly, if you consider the other integral, then you know that for this integral, this is my 2x minus 1 and this is my 2y minus 1. So if 2x minus 1 equal to half, then x will be equal to 3 by 4. and if 2i minus 1 equal to 0, then y will be equal to half. So actually this integral becomes half into beta 3 by 4 comma half. Now let me have some space here. Now we further know that our beta gamma relationship says that beta xy will be equal to gamma x gamma y divided by gamma x plus y when our xy both are positive. So we have already proved this in our previous video. So this will be equal to, by that formula, this will be equal to, if I multiply half and half, it will be 1 by 4. Okay, write that at the beginning. And beta 1 by 4, 1 by 2, that will be gamma 1 by 4 into gamma 1 by 2 divided by gamma 1 by 4 plus 1 by 2. And into beta 3 by 4 into half, so that will be gamma 3 by 4 into gamma half divided by gamma 3 by 4 plus half. Okay, so this will be equal to 1 by 4. Let me have some space again here. So 1 by 4 into gamma half. We know that gamma half is actually root pi. I hope you can remember, we derived this in our previous class. So that means if I plug in that value, this will become root pi into gamma 1 by 4, and gamma 1 by 4 plus half, that will be gamma 3 by 4 into gamma 3 divided by 4 into again gamma half, that means again root pi divided by gamma 3 by 4 plus half, so that will be gamma 5 by 4. So gamma 5 by 4. Now so we can see here straight away this gamma 3 by 4 and this gamma 3 by 4 gets cancelled, and if I multiply these two root pi, so I can write this as pi divided by 4 into, okay, so okay, let me have some space here. So we know that, further we know that gamma x plus 1 is equal to x into gamma x when our x is greater than 0. Now you can understand that this particular 5 by 4, I can write this as 1 by 4 plus 1. So gamma 1 by 4 plus 1 as per this formula can be written as 1 by 4 gamma 1 by 4. So if we implement that understanding here, I can write this thing as gamma 1 by 4 into root pi, that has been already written, so into 1 divided by 1 by 4 into gamma 1 by 4. So if you think that this gamma 1 by 4, this gamma 1 by 4 will get cancelled, and actually this 4 and this 1 by 4 will also get cancelled. So what will remain? Whatever will remain is pi. So our answer for the question is pi. That means we have got that this problem, the answer for this problem is actually pi, which we have evaluated. So you can understand that we have done it so easily using more than one property of beta gamma functions, which otherwise if you try to do in usual way would have been a bit tedious. So the answer for this problem is pi. Okay, fine. Let us solve one more problem. Show that integral 0 to 1 square root of 1 minus x to the power 4 dx is equal to gamma 1 by 4 whole square divided by 6 into under the root of 2 pi. So fine, that means we need to represent this integral in form of a gamma function. Okay, fine. So this square root of 1 minus x to the power 4. Okay, so first let us substitute x to the power 4 is equal to u. Then we have integral 0 to 1 square root of 1 minus x to the power 4 dx is equal to integral when x is 0 u is 0, when x is 1 u is 1. So integral 0 to 1 x to the power 4 equal to u. So this will become square root of 1 minus u. Now x to the power 4 is equal to u implies 4x cube dx equal to du. That implies dx is equal to 1 upon 4x cube. Now x cube means u to the power 3 by 4 du. So 1 upon 4 into u to the power 3 by 4 du. So that means this becomes into 1 upon 4 into u to the power 3 by 4 du. So if I write it in an arranged way, this will be 1 upon 4 integral 0 to 1. Let me write that u term first. So u to the power minus 3 by 4 into 1 minus u whole to the power half du. Okay, let me have some space here. Now we know that the definition of beta function says that beta xy is equal to integral 0 to 1 t to the power x minus 1 into 1 minus t whole to the power y minus 1 dt when x and y are greater than 0. So if we try to match the integrand that we are having with the integrand that is there in the beta form, so then we can think of this as our as our x minus 1 and this as our y minus 1. So if we think x minus 1 is equal to minus 3 by 4, then x will be equal to 1 by 4. And if we think y minus 1 is equal to half, then our y will be equal to 3 by 2. So that means this integral is actually 1 upon 4 beta 1 by 4 comma 3 by 2. So this now we know that as per the relationship that beta xy is equal to gamma x gamma y divided by gamma x plus y when xy are greater than 0. If we use this relationship, we can write that this integral is equal to what? This is equal to 1 upon 4 into gamma 1 upon 4 into gamma 3 upon 2 divided by gamma 1 upon 4 plus 3 upon 2. Fine. So this will be equal to 1 upon 4 into gamma 1 upon 4 means that, and gamma 3 by 2, you know that this can be written as gamma half plus 1. That means this can be written as half into gamma half divided by gamma 1 upon 4 plus 3 upon 2. That means what? That means gamma 7 by 4. So this. Now let me first have some space here. So this can be written as equal to 1 upon 4. Now gamma 1 upon 4 into half into gamma half means root pi. Now you know that gamma 7 by 4 can be written as gamma 3 by 4 plus 1. So that means this will be equal to 3 by 4 into gamma 3 by 4. Now this. So the whole thing becomes this. That means if we do a bit simplification, this will become 1 upon 4 into 4 by 3 into half. So that means this will become 1 by 6 into root pi. So that means if I write it, this can be written as square root of pi divided by 6 into gamma 1 upon 4 divided by gamma 3 upon 4. Now let us look at the question, just what we have to prove. We have to prove that this given integral is equal to, in the numerator we are having gamma 1 by 4 whole square. Okay, fine. Let us do one thing. Let us multiply the numerator and denominator by gamma 1 upon 4. So this will be equal to root pi divided by 6 into gamma 1 upon 4 whole square divided by gamma 1 upon 4 into gamma 3 upon 4. So now if it is if there is 2 in the denominator, for example gamma half, gamma 3 by 2, gamma 5 by 2, we know how to calculate this. So I don't have such a situation here. I have gamma 1 upon 4 into gamma 3 upon 4. So how to tackle this? If you remember, we discussed a formula in our previous discussion, and I showed you at the beginning of this class also that there is a formula which says gamma m into gamma 1 minus m is equal to pi into cosec m pi, where this 0 less than m less than 1. If I have such a relationship, then gamma m into gamma 1 minus m is equal to pi cosec m pi. I have such a formula when m is 0, lying between 0 and 1. So now can you tell me, can I use this formula in this denominator? Absolutely correct. If we choose m equal to 1 by 4, actually in this denominator m is nothing but m equal to 1 by 4. If I consider m as 1 upon 4, so that means I get gamma 1 upon 4 into gamma 1 minus 1 upon 4 means 3 upon 4 is equal to pi cosec m pi, means 1 upon 4 into pi, so pi by 4. Now here m is 1 by 4, which lies between 0 to 1 also. So this condition is also satisfied. So this value is actually nothing but pi into cosec pi by 4. So that means I can write this as equal to square root of pi divided by 6 into gamma 1 upon 4 whole square divided by gamma 1 upon 4 into gamma 3 upon 4. That means pi into cosec pi by 4. Now can you tell me what is the value of cosec pi by 4? Absolutely correct. That is root 2. So this will be equal to root pi divided by 6, root pi divided by 6 into gamma 1 upon 4 whole square divided by pi into root 2. So you can understand that if I cancel out this, I will be having root pi at the denominator. So that means what I am getting, if I simplify, I am getting gamma 1 upon 4 whole square in the numerator divided by 6 into root 2 into root pi. That means 6 into under the root 2 pi. So this. Let us see now what is to be proved. Yeah, exactly this. So we are done. So hence proved. Hence proved. Or hence we have shown our whatever is to be shown. So that's it. So that's it. So that means you can understand that actually this formula at time becomes very, very useful. Means that the formula that gamma m into gamma 1 minus m is pi cosec m pi. This at times will be very, very useful. Okay, now let us solve one more problem. Show that integral 0 to 1 x to the power minus 1 by 3 into 1 minus x whole to the power minus 2 by 3 into 1 plus 2x whole to the power minus 1 dx is equal to 1 upon 9 to the power 1 by 3 into beta 2 by 3 1 by 3. Now that means we need to represent this integral in the left hand side as a beta function. That is tricky. This problem is a bit tricky, not so easy or obvious like the previous problems that we solved. The substitution needs to be chosen very, very carefully. We need to be very, very careful while choosing the substitution. Now the way that I will do it, okay, let us substitute x upon 1 minus x equal to at divided by 1 minus t, where a is a constant to be so chosen that the given integral becomes a beta function. Let us do this substitution in integral 0 plus epsilon to 1 minus delta. If you have to understand why I am taking the limits of the integration in this way, you have to refer to my previous video on improper integral. I hope you all have seen that, so I am not repeating here. If you have any doubt, just go and check my video on improper integrals. So integral 0 plus epsilon to 1 minus delta x to the power minus 1 upon 3 1 minus x whole to the power minus 2 upon 3 1 plus 2x whole to the power minus 1 dx, where my epsilon and delta both are greater than 0 as discussed as I've already discussed why they are greater than 0 in my previous video. So I am substituting this thing x divided by 1 minus x equal to at divided by 1 minus t. Now I have not yet fixed the value of a. I will fix the value of a later depending on what we get in after the calculation, and my objective is to get a beta function. The value of a is to be so chosen that I get a beta function in this. So yeah, if we do this substitution, then in this integral, then what we will get, actually see here x divided by 1 minus x equal to at divided by 1 minus t. Now this implies that x into 1 minus t will be equal to 1 minus x into at. So this means if I find out x from this, so I will be getting x is equal to at divided by 1 minus t plus at. So x will be equal to this. Yeah, perfectly all right. X will be equal to this. Therefore, if I find out, therefore I can write that is, can you tell me what will be dx if this is my x? So dx will be equal to, what will be dx? Exactly a dt, if you do this calculation, divided by 1 minus t plus at whole square. This will be my dx, 1 minus t plus at whole square. That means I can even write 1 minus, if I take this t common, 1 minus a into t whole square. Anyway, so if I plug in all these values here, this consideration, so what I'll be getting as this integral will be equal to now will be equal to integration. Now when x is epsilon, okay fine, if we do one more calculation in a similar way, instead of finding out x, if we find out t in terms of x, so this will also give us, from this relationship we can further get that t will be equal to x divided by x plus a minus ax. You just can calculate t from this. When x is epsilon, t will be equal to epsilon divided by epsilon plus a minus a epsilon, and when x is 1 minus delta, t will be 1 minus delta divided by 1 minus delta plus a minus a into 1 minus delta. Actually a will get cancelled, plus a minus a. So okay, let it be as it is. So yeah, this will become, the integrand will become, it will be a lengthy expression, so be careful while writing this. So this will become at divided by x to the power minus 1 by 3. So at divided by 1 minus t plus at whole to the power minus 1 upon 3 into 1 minus x whole to the power minus 2 by 3. So that will become 1 minus t whole divided by, if you do the calculation, it will become 1 minus t whole divided by 1 minus t plus at whole to the power minus 2 by 3. Because you can understand, if x is equal to this, then 1 minus x will be equal to 1 minus t divided by 1 minus t plus at. Actually at will cancel out from the numerator if you calculate 1 minus x, that is the only thing. Into, now I don't have any space to write in the right side, so okay, let me write here 1 plus 2x whole to the power minus 1. So 1 plus 2x whole to the power minus 1 will look like 1 minus t plus 3at, correct, 280 plus 80, so 380 divided by 1 minus t plus at whole to the power minus 1 into dx is equal to further a dt, as we have already calculated dx here, a dt divided by 1 minus t plus at whole square. So we have already written, so actually now this becomes, the whole thing becomes my integrand after this substitution. I hope everything is clearly written. So that means if I write it once again by calculating the respective terms, and let us consider whether we can simplify this expression a bit or not. So this is equal to, actually integral, the lower limit will become epsilon by epsilon plus a minus a epsilon, and this will be 1 minus delta divided by, a will get cancelled, so 1 minus delta plus a delta. Acha. Now if we consider this numerator of this entire calculation, then you can understand that the numerator will become, say, let us calculate one by one, a to the power minus 1 by 3 into a. So a to the power minus 1 by 3 into a, that means a to the power 2 by 3. So first let us write a to the power 2 divided by 3. Be very careful while doing this calculation. Now there is no other t, only t. I don't have any t in the numerator. That is only t that I can write here. So I will write here t to the power minus 1 upon 3. Okay, fine. Now what are the other terms in the numerator? 1 minus t. Okay, so I have 1 minus t to the power minus 2 by 3. Fine. Let us write that. I don't have that term anywhere else. 1 minus t to the power minus 2 by 3. Very good. Minus 2 by 3. And now the question is, okay. So, and one more thing that I'll have here is 1 minus t plus 3at whole to the power minus 1. Yes, 1 minus t plus 3at whole to the power minus 1. Very good. So this is in the numerator. So what will be there in the denominator? In the denominator I have 1 minus t plus at whole to the power minus 1 by 3 into 1 minus t plus at whole to the power minus 2 by 3 into 1 minus t plus at whole to the power minus 1, and I have the another term from this one, that is 1 minus t plus at whole square. I don't have any other terms left, so dt. That is what I am having. The expression is a bit lengthy, but if you look at the denominator carefully, the power of this term 1 minus t plus at sums to be 0. Minus 1 by 3, minus 2 by 3. So that means minus 1, minus 1, minus 2, plus 2. So that is 0. So your denominator is actually 1. So we got a pretty simple integration. Means the form, not pretty simple, but simpler than what we were actually seeing so long. So epsilon divided by epsilon plus a minus a epsilon to 1 minus delta divided by 1 minus delta plus a delta. And now the thing becomes pretty simple. It is a to the power 2 by 3 into t to the power minus 1 by 3 into 1 minus t whole to the power minus 2 by 3 into 1 minus t plus 3at whole to the power minus 1, and in the denominator I will have, if I multiply all the terms in the denominator, I will get 1 minus t plus at whole to the power 0, that is 1. So I can write dt. So this is what I have got so far. So this is the simplified version of the integral after our substitution. Yes. So now what is our objective? Our objective is to find out, or what I wrote when I started, when I had chosen the substitution. First, if you consider this a, what I have said about this a, I said that this a is a constant to be so chosen that the given integral becomes a beta function. Now the given integral got reduced to this form. Can you tell me for which value of a this integral will become a beta function? See, if you consider a in this portion, it is not going to create any problem because this is a constant. I will take it out of the integration simply. Now where else a is occurring? Else a is occurring at this position. Now can you tell me what should be the value of a, because see, this is t to the power something, 1 minus t to the power something. I don't have any problem with that, because that is this t and 1 minus t is in the form of is as required in beta function, but the problem is with this particular term. So can you tell me what is to be chosen for a? See, I have to choose a in such a way, means the best way to think is that I have to choose in such a way that this term becomes 1. This entire term becomes 1. So keeping in mind what is to be chosen, or in other words, I can choose a in such a way that t gets cancelled. So I get 1 to the power minus 1, that is 1. So eventually the integral will be similar to what we see in beta function, excepting this limits. So that we will take care of. First let us deal with the integrand. Yes, absolutely correct. A has to be chosen as 1 by 3. So let us choose a equals to 1 upon 3 and letting epsilon tends to 0 plus and delta tends to 0 plus, we get, okay, to write what we get, okay, so if we let delta tends to 0 plus and epsilon tends to 0 plus, this integral will become integral 0 to 1, whatever is the integrand. And if we let delta tends to 0 plus and epsilon tends to 0 plus, so epsilon tends to 0 plus means this will become 0, because it will be 0 by a is 1 by 3, so that is 0, and delta tends to 0 plus means this will become 1 by 1, so that is 1. So this will also become 0 to 1. So if we write everything, if we do these considerations, then integral 0 to 1 x to the power minus 1 by 3, that means I am writing the left hand side, into 1 minus x whole to the power minus 2 by 3 into 1 plus 2x whole to the power minus 1 dx, that is the left hand side from where we started. If we apply this consideration in both the sides, so this is the left hand side, the limit will become 0 to 1, equal to, now in the right hand side, as we can see in this step, my limits will become 0 to 1, okay, a to the power 2 by 3, so 1 by 3 whole to the power 2 by 3 into t to the power minus 1 by 3. So t to the power minus 1 by 3, 1 minus t whole to the power minus 2 by 3, and this will become now 1 dt. So that means if we write in a more arranged way, this can be written as 1 by 3 whole square, that means 1 by 1 by 9 to the power 1 by 3, so 1 by 9 to the power 1 by 3, integral 0 to 1 t to the power 1 by 3, t to the power 1 by 3 can be written as t to the power 2 by 3 minus 1 and 1 minus t whole to the power minus 2 by 3. I can write this minus 2 by 3 as 1 by 3 minus 1. So this dt. Now remember, we know that beta xy, I hope by this time you have remembered the formula. This is equal to integral 0 to 1 t to the power x minus 1 1 minus t whole to the power y minus 1 dt when your x and y are greater than 0. So can you tell me, if I match the integral in the right hand side with this beta function, what I am getting? I am getting 1 divided by 9 to the power 1 by 3 into beta 2 by 3 comma 1 by 3. So this, now what we had to prove, what was our question? Yeah, this. Okay, we have proved, we have showed whatever was supposed to be shown. So hence proved. I feel so good when I can write this line, hence proved. This is my favorite line. So hence proved. So this, so you can understand that This is a bit tricky problem, so you have to be very careful while solving this kind of problem. While doing the calculation, you need to be very careful. If you make any mistake, then your conclusion may be wrong. So that's it for this problem. Okay, now let us solve one more problem. Using sine pi by a into sine 2 pi by a into sine 3 pi by a, in this way into sine a minus 1 pi by a equal to a divided by 2 to the power a minus 1, where a is a positive integer greater than 1. Prove that gamma 1 by a into gamma 2 by a into gamma 3 by a etc. into gamma a minus 1 by a is equal to twice pi whole to the power a minus 1 by a whole to the power half. And gamma 1 by 9 into gamma 2 by 9 etc. gamma 8 by 9 is equal to 16 by 34 into pi to the power 4. Okay, now if you look carefully, the second part of the problem is can be just obtained from the once we can prove the first part, because if you plug in a equal to 9 in the first part as it appears, you will get the second part. So main task of the problem is proving the first part, because the second part is just a supplement for a equal to 9. Anyway, let us solve it. The problem, the problem may look difficult, but believe me, it's a very simple problem. It's a very simple problem. Once you identify which formula you have to apply, or how you have to proceed. See, we need to prove, if I consider the first part, we need to prove that the left hand side is equal to square root of whatever is in the right hand side. So that means we can think in other way, that if I try to prove that the squaring the left hand side expression, if I can bring 2 pi whole to the power a minus 1 by a, then also my job will be done. Okay, so let us find out gamma 1 upon a into gamma 2 upon a into gamma 3 upon a, in this way gamma a minus 1 upon a whole square. Let us see what I get out of this. So the whole square of this means I can think that I am having gamma 1 upon a into gamma 2 upon a, in this way gamma 3 upon a. Actually, can I write this as gamma a by a minus 1 by a? So that means 1 minus 1 by a. Can I write in this way? So this into the same expression, that is gamma 1 upon a into gamma 2 upon a, in this way gamma 1 minus 1 upon a, the same expression. And this will be written as, now let us do one thing. Let us group in this way the products in a way that this gamma 1 upon a is grouped with this gamma 1 minus 1 upon a. Similarly, I will have some gamma 1 minus 2 upon a somewhere before this, so I'll group this gamma 2 divided by a with this whatever term is there as gamma 1 minus 2 upon a, and this gamma 1 minus 1 upon a, let us group it with this term gamma 1 by a. So if I consider all these things and if I write in that sort of an arrangement, then what I'll be getting as gamma 1 upon a into gamma 1 minus 1 upon a, then gamma 2 upon a, the second term from the last in the second product will be gamma 1 minus 2 upon a, In this way, if I go till the end, so I will write gamma 1 minus 1 upon a, the last term of the first product, into the first term of the second product, that means this, into gamma 1 upon a. So this, so we have got this. Now what is the advantage? The advantage is, if you think that we have used a formula which I discussed also in the list of formula that I had given you. Yes, this point number 8. If you think about this one, this point number 8, then gamma m into 1 minus m, for that I have a formula. When m is 0 less than 1, m less than 1. But our case is, in our case what we are having is, in our case we are having that this a is an integer, so a is a positive integer, so 1 upon a will lie between 0 and 1. So that means I can apply the formula that whatever we have seen, that gamma m into gamma 1 minus m is equal to pi cosec m pi. We can use this formula, and this is applicable when 0 less than m less than 1. Now since a is a positive integer, 1 upon a will be lying between 0 and 1. So if I use this formula, then I'll be getting this as, so pi into cosec m pi, here m is 1 upon a, so 1 upon a into pi, into pi cosec 2 upon a into pi. In this way, pi cosec again the same thing, a 1 minus a is now my m, so that means a minus 1 divided by a into pi, because you can understand that this 1 by a can be written as 1 minus 1 minus 1 by a, right? So again by the same logic, if a is a positive integer, 1 by a lies between 0 to 1, so 1 minus 1 by a also will lie between 0 to 1. So pi into cosec a minus 1 divided by a into pi. So fine. So fine, if we now so okay, let me write the logic here. Since I'll simply write, since 0 less than 1 upon a less than 1, so I get this due to this reason. Therefore can you tell me how many pi's we are having actually here? How many number of pi we are having here? How many number of terms we are having here? Be very careful. Answer me very carefully. How many pi's we are having here, or how many terms like this we are having here? So 1 term, 2 term, then third and fourth. How many terms I'll be have? Exactly correct. I'll be having total a minus 1 number of terms here. So I will be getting here, I'll be getting here pi to the power a minus 1. So that means a minus 1 number of pi's I'll be having. So pi to the power a minus 1 into, now cosec pi by a into cosec 2 pi by a etc. into cosec a minus 1 into pi by a. So can you tell me what will be that? What will be that? What is the question given to us? We have been given that sine pi by a into sine 2 pi by a into sine 3 pi by a etc. into sine a minus 1 pi by a, that is a by 2 to the power a minus 1. So now that means cosec pi by a into cosec 2 pi by a into cosec 3 pi by a, etc. That will be 1 divided by this sin pi by a into sin 2 pi by a into sin 3 pi by a, etc. So that will be equal to 1 divided by a by 2 to the power a minus 1. So this can be written as equal to, okay. If I write this, this can be written as into 1 divided by sin pi by a into sin twice pi by a. In this way, sin a minus 1 by a into pi, sin a minus 1 pi by a. So this, now as per our condition given, this will be equal to, let me check the value once again. So 1 by a by 2 to the power a minus 1, that means 2 to the power a minus 1 by a. So that means this is equal to pi to the power a minus 1 into 2 to the power a minus 1 divided by a. So we have got this. That means I can further write 2 pi twice pi whole to the power a minus 1 divided by a. So now can you tell me what I had to prove? 2 pi whole to the power by a. So yeah, so the whole square, gamma 1 upon a into gamma 2 upon a, etc. whole square is equal to this. So therefore what we are getting, we are getting that gamma 1 upon a into gamma 2 upon a, etc. into gamma a minus 1 upon a will be equal to twice pi, it will be twice pi whole to the power a minus 1 divided by a whole to the power half. So hence proved, my favorite line, hence proved. Now hence proved. Now the second part, as I told you earlier, that the second part can be simply plugging in a equal to 9 in the first part. So that is pretty simple. So number 2, putting a equal to 9, putting a equal to 9, we get gamma 1 divided by 9 into gamma 2 divided by 9, etc. into gamma 8 divided by 9 is equal to 9. So twice pi divided by whole to the power 9 minus 1. So 8 divided by 9 whole to the power half. So that means if you do the calculation, it will be 3 and 8 to the power, that means 4, 8 whole to the power half. Actually this half is written below 8, so I think I should write it like this, this whole to the power half. So actually you can understand that the denominator will be 3 and 2 to the power 8 to the power half, 2 to the power 4 means 16, pi to the power 4 divided by 3. So yeah, we got the answer. Again my favorite line, hence proved. So fine, we have solved 5 different types of problems. Actually I don't consider these as 2 problems, so 5 different kind of problems where we have used mainly one or more of this 8 key points that I had jotted down at the beginning of this class. So yeah, this is how you can solve problems related to beta gamma functions. Now let me leave some problems for you to practice. Yes, these 3 problems. The first one, show that integral 0 to infinity e to the power minus a square x square dx equal to 1 upon twice a root pi. Second one, show that integral 0 to 1 dx divided by 1 minus x to the power 6 whole to the power 1 by 6 is equal to pi by 3. Third one, evaluate integral 0 to 1 x cube into 1 minus x square whole to the power 5 by 2 dx. So pause the video, copy these problems and quickly solve them. Let me know your answers and your findings, or if anything you would like to say in the comment section below. I will be waiting to hear from you. That's it for today. See you again in the next video. Take care.